Hello, Bimbo. Can you please share your slides?
Sure. Okay, good morning, everyone. My talk is titled Using Contact Information to Map a Cluttered Scene and Retrieve an Object. The motivation for this work is the necessity of having robots that can work in cluttered scenes, in scenes that contain a lot of debris that are very uncertain. And like the previous speaker was saying, in this kind of scenes, you create occlusions. It becomes difficult to use cameras, to use vision. So we also rely on force information. The goal here is to if you see the picture on the right, to pull an object that you don't know the shape of from an environment that you don't know the shape of either. The force information that we use is the force torque sensor on the robot hand effector. And the strategy pretty much consists of generating and populating two occupancy maps, two 3D maps, one of which maps the environment, so maps the obstacles on the environment and is fixed to the world, and the other one moves around with the end effector and tries to reconstruct the geometry of the object that you're trying to pull. Each probability map informs the construction of the other, meaning that the more you know about the environment, the easier it is to reconstruct the object, and vice versa. We do this through implementing two probability laws. One we apply when we are pulling and we feel a force, so we feel that there's a contact between the object and the environment. There was a collision. The other is, we use when we are not feeling any force. So if you're trying to pull something and you don't feel any collision, you gain some information from that fact. The first probability law that we use so you can see here, we try to put laser pointer. So you see here, you're trying to pull this gray object away from this environment that has these two pegs, this red and this blue peg. And at some point you hit here, right? When you hit here, you feel a force, and you can use these equations here on the right. Under some assumptions, you can tell what's the line of action of that force. So you don't know exactly where it collided, but you know that somewhere along that line, that's where the collision happened, right? So along that line that we discretize into like little voxels, so little cubes, there's got to be necessarily a point, at least, where there's an obstacle. So there's an occupied voxel in the environment, and there's also part of the object there. So that's why you have a collision. They overlap, and that's why you feel a force. So we use the prior knowledge of the prior belief on the occupancy of those voxels along the line of action, both on the map of the environment and on the map of the object, to continuously update the belief and populate that map with the probabilities that they are occupied. And this is the formula. So what we're trying to do is we're trying to find the updated probability of occupancy at point P. And we do this by counting the cases of simply like a frequentist approach here. So first we count all the possible cases. So somewhere along that line, there's got to be two overlapping voxels, N and N prime. These are, you can think N is a point in the environment. N prime is that coincident point expressed on the map of the object, or vice versa. It doesn't matter. Like, this is kind of what we do in one, we do in the other. So there's got to be two overlapping voxels there that are both occupied along that line. We do this like we sort of use some probabilistic, like the Morgan laws, to make the calculation easy. So what we do is we find the probability that no point is occupied along that line, and we subtract it from 1. And then we fill the denominator here. To fill the numerator, we find let's say the cases that we're interested in, right? So the cases where P is occupied. P is occupied if P and P prime are occupied and the contact happened there, right? But we also must consider the cases where P is occupied and P is free and the contact happened somewhere else along that line. So that's that section there. This is how it works in practice. So you have a map here that is fixed, and the robot is moving around, and every time it hits, you see this red line, and you apply that probability law. As this line starts intersecting more at particular points, you start increasing your belief that this point here is occupied. And also on the object, you can, after all these contacts, you can have a good idea that this one is occupied, and then somewhere along here is also occupied. So this is how it works in a real setting. I'm just going to play it again. So you see after the first few hits, you start creating these lines. These lines start intersecting at particular points. So here I just got rid of, I'm just showing the voxels which I believe are occupied above a threshold of 50%. The white one is where you believe there's an obstacle. It kind of matches. And the red one is where you believe there is object. So now what you're trying to do is you're trying to find a trajectory that goes from where, that pulls this object out without ever overlapping between those two. So this is what's happening here. So it retrieves the object. When you're in free space, this is also informative, and we use another probability law that kind of follows the same idea. So first we count all the admissible cases. So all the admissible cases here is more simple. So there's no overlapping voxels. You don't feel a force, so nothing is in collision. So you know there's no point P and P prime which are both occupied at this particular pose. And now the cases we're interested in, where P is occupied, are only the cases where P is occupied and P prime is free. So this is a bit simpler. And this works. So you see there's just like a slight difference. There's like a little animation here that shows how it changes. In this, for example, if you're not feeling any force and you have two voxels which are likely occupied that are overlapping each other, you know this cannot be the case, right? So you have a big drop in the likelihood there. On the other hand, if the overlapping one is very likely occupied, the other one is likely free, then it almost doesn't change because that doesn't really go against what we thought. These are results in simulation. So in simulation, we get a bit better force measurements. We're trying to pull this object that we don't know the shape of to a region over here. Start going around. You can see the white things are where we think there's an obstacle, and then the red and green are the ones we think there's an object. So at some point, once you know enough about the geometry of the object and enough about the object, the geometry of the environment, you're able to find this trajectory that avoids all collisions and pulls out the object successfully. So that's that. Thank you for watching.